My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 552. In this lecture, we will try to understand the bias variance trade-off of neural networks or multi-layer perceptron. The first thing is, as the number of layers increase, what happens? You have more weights or parameters that we are eventually learn for the model. So as we have more weights, there is a higher chance of overfitting, isn't it? Higher chance of overfitting of your model, which means as number of layers increase, we could have problem of high variance. So in a nutshell, as a number of layers increase, you will end up a case of high variance. This is first point. My second point is, if the number of layers are too few, let's take the limiting case. Let's say if you have one layer neural network, simple one layer neural network, nothing. Simple one layer neural network is nothing but one layer neural network with one layer neural network with sigmoid activation function. That's nothing but logistic regression, isn't it? It is nothing but logistic regression, and logistic regression literally is nothing but a plane that is trying to separate positive points from negative points, isn't it? What is logistic regression? It's basically a plane that separate positive points from negative points. So if you have very few layers, which means you have very few weights. Few layers means what? It have few weights, which means you run into the problem of high chance of underfitting, isn't it? And underfitting basically, what is underfitting? Underfitting basically means high bias, isn't it? What's the meaning of underfitting? It means high bias. So the bias variance trade-off with respect to neural network or multi-layer perceptron, for that matter, because neural network, there are lots of types of neural networks. Now let's just focus on multi-layer perceptron, isn't it? As a number of layers increase, you have a problem of overfitting, isn't it? You have a problem of overfitting because you have more weights. Reason is you have more weights that you can fine tune. For your training data. If you have more weights, let's say you have 1000 data points, and let's assume you have 1000 weights. 1000 data points means what? 1000 weights, because I have more weights to fine tune and more weights to fine tune and tweak, isn't it? I can make my 1000 weights fit so well to these 1000 data points, so that I could easily overfit, isn't it? Instead of 1000 weights, let's assume I have only 10 weights, isn't it? Then amount of fine tune that can do for 10 weights is much lesser than 1000 weights. So if I have fewer weights, then I have higher chance of underfitting. Fewer weights means higher chance of underfitting my model. So similarly, logistic regression has a bias problem more than high variance problem, isn't it? Logistic regression has a bias problem more than high variance problem because it is very similar model with very few weights, isn't it? Since it has fewer parameters or weights, it has high chance of underfitting, isn't it? It is high chance of underfitting or high bias problem. You might wonder, and typically multi-layer perceptrons don't have problem of underfitting. Multi-layer perceptron don't have problem of underfitting as much. They typically run with the problem of high variance, isn't it? So typically multi-layer perceptron, because you have multiple layers, you have a problem of overfitting or high variance that you are typically run into. What is the solution? What is the solution for this? For this high variance solution is what you have to do. You have to add regularization. So one way we can do here, add regularization to the problem. Your loss function here, for which we are computing the derivative. What is my loss function? Summation of I equal to 110 loss of yi comma yi cap. In addition to loss, we will also have L is a loss function. It's a function of yi comma yi cap. In addition to having a loss, we will also have regularization, like L2 regularization. How does L2 regularization looks like? Take each of wkij summation over all ijk wkij whole square, isn't it? I can have L2 regularization or L1 regularization. In a nutshell, make my loss summation over all the losses, isn't it? Sigma phi loss of phi plus lambda into L2 regularizer. Of course, I have to put some weight on L2 regularization, and higher the weight here, larger my lambda, I will have loss. I will have less overfit to the problem, isn't it? Larger the lambda, I will have less overfit problem. Just like in logistic regression or linear regression, we are adding regularization term, isn't it? If you use L1 regularization instead of L2 regularization, it creates a sparsity, isn't it? What does sparsity means? There will be some weights which will become 0, isn't it? Which means if weight is 0, what happens in neural networks perspective? The edge, weight is 0 means the edge is disconnected. For example, just see, for example, if this weight is 0, this will be disconnected. If this weight is 0, this will be disconnected. If this weight is 0, this will be disconnected. If this weight is 0, this will be disconnected. And the edge is disconnected. It is equal to say that edge does not exist. In a way, if we use L1 regularization, you will create sparsity, that is wkij equal to 0. Multi-layer perceptron becomes sparse. So often seen problem in multi-layer perceptron is high variance and fixed by standard L2 or L1 regularization and fits perfectly into the optimization framework, isn't it? Because remember, what is a multi-layer perceptron? You can think of it is multi-layer generalization of your logistic regression or linear regression. So all the mathematical machinery of L1 regularization and L2 regularization that we learn is perfectly valid here. That's the fun part of optimization. Here lambda is a hyperparameter, isn't it? Larger the lambda means, what is the meaning of larger the lambda? Low variance. Number of layers increasing means variance will also increase, which results in high variance problem, especially when you are using sigmoid unit. If your sigmoid unit, you can, if your activation function is sigmoid unit, you can easily run into the vanishing gradient problem. So keeps your number of layers sensible. I request all of you to go through this lecture and try to understand what is bias variance trade-off in multi-layer perceptron. Just revisit this lecture once or twice. There may be few terms which may not be able to follow, don't worry about it. We will discuss all these things in detailed manner in future lectures. Just now, time being, just understand what is bias variance trade-off of multi-layer perceptron. This is lecture number 552. In my next lecture, that is lecture number 553, I will start decision surfaces playground. Thank you very much.